Hi, my name is Robinson Navas. I'm a senior here at Fresno State. My major is electrical engineering. Our project is to design an RFID mesh network, and my part of the project is to write the code for the Arduino.
Hello, my name is Jonathan Fernandez. I'm a senior here at Fresno State. My major is electrical engineering. The part of the project I worked on was the transmitter for the RFID and the USB RFID reader.
Hello, my name is Pedro Navarez. I'm a senior and major is electrical engineering. My part of the project was to design the receiver for the RFID reader and antenna.
An RFID system with the capability to determine location of RFID tags using a network of RFID readers does not exist in the ECE department. Currently, a lot of companies are losing millions of dollars because they do not have a good system to keep track of their inventory.
The objective of this project is to create an RFID system that is able to locate and track the location of RFID tags in certain zones using a network of RFID readers. We're also going to design and implement our own RFID reader. This is the system diagram that we will be using for this project. As you can see, each RFID reader represents a zone that can detect RFID tags. The RFID readers are connected to the backend server via a USB serial port.
Okay, so this is a system block diagram that we'll be using for our system. It's a block diagram of an RFID reader. As you can see, there's a host system that sends a signal out through a processor, which will send it as a square wave. The square wave will be transmitted through a transmitter and changed into a sine wave, and we're going to have it sent through an antenna to find any tags nearby, which will send a signal back if one's found to a receiver, and all that will come back to the system diagram, to the system host to interpret the message.
For the system we designed, we're going to be using the Arduino Uno board. The reason why we chose the Arduino Uno board is because it has 14 input and output pins that we can use. It also has a built-in 6 pulse width modulation outputs with a built-in 16 megahertz oscillator. It also has an easily accessible USB connector.
Okay, well, as you can see here, this is our system diagram that we'll be using. At the top, you can see that is the transmitter circuit, and at the bottom we have the receiver circuit that we'll be using. These have been tested in multi-sim networks.
Is the RFID ID20 reader which we'll be using for this project. The ID20 will read the tags and locate its location. This one is very useful because it's very easy to connect to the microcontroller that we're using, and it's easy to also program to read the tags and locate it. Turn on the Arduino board and show that in fact the ID20s do read the tags. One, which as you guys can see is the yellow LED, and is always lighting up, and that's because it's checking that the reader 1 and reader 2 are active, and they're always scanning to detect the tags. Now I'm going to place one of the passive tags in front of RFID 1, and as you guys can see, the second LED, the green one, starts lighting up, and that's just telling us that reader 1 is detecting the tag in front of it. Now I'm going to place one of the other tags in front of the second reader. Now we can see that the red
and yellow LEDs are lighting up, which corresponds to each of the tags in front of the readers. Now if I go ahead and remove the tag in reader 1 and replace it with a different tag, we can still see that the readers are detecting the tags and lighting up the corresponding LED. In this case is the green and red. Now I'm going to show you guys the code and what is being displayed when the RFID readers detect the tags. As I mentioned earlier, the RFIDs scan for tags every few milliseconds, and it detects if the tag is still in place. And this section over here is the loop that is constantly looping and resetting the readers. I also have a counter, which on this one, if I is equal to 0, then it's gonna activate the RFID reader number 1, and then it's gonna increment the counter, and in the second time it's gonna check if I is equal to 1, and then it's gonna activate the second RFID reader to read the tags. This section over here is just to store the tag ID. The last part of the code is for the multiplexer, which this side right here is just the 16 channels, and I created an array in binary which goes from 0 to 15, and that will give me the option to connect more RFID readers to the multiplexer.
This first video will show me with the RFID tag putting it in the zone of the RFID reader, and the RFID reader will make a noise indicating that the RFID tag is within its read range. This next video will show me using the TerraTerm software for the use of creating zones with an RFID reader. Each zone will have its own window. There will be 4 windows, each window representing a zone. When an RFID tag is in that zone, it'll display which tag it is, and if it's in the zone, it'll continuously check, see how long it's been in the zone. This last video shows me using the USB RFID readers with the TerraTerm software with multiple RFID tags. I'm going to use 2 tags at a time in 2 different zones, and I'm be able to see how long the tag has been in the zone and which zone they are in. So you could see me doing zones 1 and 2 first, and then zones 3 and 4 with 2 different tags. From this video you can see that we were successfully able to monitor 4 different zones using the USB RFID reader. Now of course the read range was only about 2 inches. If you were to have a larger read range such as a warehouse, it would need to be in the 900 megahertz range. The part I'm working on is the transmitter of the RFID. What we got here is we got the RF choke stage right here. This stage right here takes the square wave input, 125 kilohertz square wave input, eliminates the high frequencies and gives us a sine wave. And then this half bridge right here, it amplifies the signal in order to be sent out the antenna right here. That's our antenna output. And as you can see, we have our input is a square wave, and then our output is an amplified sine wave.
Okay, so for my part of the project, I'll be using the antenna, which is this, which will be connected to the RFID receiver. The receiver will function as a device that interprets the signal that comes back from the antenna once it reads a tag or one of the RFID cards. Okay, so for the first part of the receiver, once it's connected to an antenna, we're going to have the 125 kilohertz signal coming from the transmitter, which will be covered by John in his video. The signal will come through this cable right here, which right now is connected to the function generator to generate the 125 kilohertz signal that we need, and it will pass through the antenna, which is connected and functions as an inductance between the antenna and these inductors right here. Now what we want to happen is we want the antenna to read the tag and interpret it in a way to give us a modified signal. Is the filtering stage. The filtering stage has 3 parts. The first 2 parts act as the same. They increase the gain to they act as a bandpass for the gain between 10 and 20 kilohertz, which limits off what we want pretty much. The last part is a low pass Butterworth filter, and that will increase the gain once more between the 10 20 kilohertz and knock off any high frequency which we don't want, which includes the 125 kilohertz signal, the carrier signal. As you can see, the function generator is already set to 125 kilohertz. The power supply is already set to 12 and 12. We're going to need 2 different signals, negative 12 and the 12. And lastly, we got the oscilloscope. Okay, so first off, I'm going to show you that the antenna by itself does give us back the signal that's being inputted when there's nothing present. Connect it real quick. So now it's reading right from the entrance of the antenna. As you can see on the oscilloscope, we're getting a perfect signal coming back out, which is the 125 kilohertz. This is what should be happening when there's no tags present. The next part of this should be going through the rectifier, and once past the rectifier, go to the filters, and lastly through the comparator. In simulation, the filters and the comparator stage work just fine, as can be seen here on the computer. This is the comparator stage where we get square signal back out. For the filtering stage, we get nice results in simulation. The problem for this project not functioning correctly is that the rectifier does not seem to want to rectify. It doesn't separate the comparator from the output. Also, the antenna, when placed next to a tag, does not give us back a modulated signal as it should. As you can see here, placing a tag. As you can see, nothing comes out. As you can see, nothing. We're supposed to get a modulated signal using the carrier as a carrier and envelope signal. This just tells me that the antenna was either constructed wrong or the number of turns is not functioning correctly. Okay, this concludes our video of our senior design project. Thank you for watching.
And a special thank you goes out to the Louds College of Engineering and to the undergraduate research studies at Fresno State for funding our project.